here in the last lecture. We stopped here in the slide number 121. We are discussing the inversion. So inversion is bad for us because inversion pushes the pollutants to the ground areas. So the temperature increases with the elevation is the lapse rate. So the plume types, there are six different types of plumes. So the first one, it looks like the temperature decreasing with this. So this is something in this case good for us at some point. So it's called strong lapse condition. So you see the pollutants coming here, going up. So this area is safe, this area is not safe, this area is not safe. So maybe something happening, inversion in this area, inversion in this area. And the next one looks like this is the lapse rate, and the temperature is here. Looks like it was here and it was here. So it's not following this. So that's why it has an effect a little bit. But you see this area still have a space for the people in around here. So this could be kind of safe. Weak lapse condition, coning, it become kind of cone. So if the cone becomes worse in this case, comes down here, then it's bad for us. And this one, you see this one is temperature is like say this is temperature, this is the lapse rate, and this is the temperature. Temperature is increasing with this, but in this case inversion condition, but fanning, somehow it's becoming fanning. So in here this one is looks like increasing and decreasing. That's why it started increasing then decreased. So that's why it's not in here, right? It's not coming to the outside. It's inversion below. So lapse a lot. So this is to some extent good for us. So how about this one? This one looks like initially it started with decreasing, then it goes up. So that's why you see it's happening something like that. So this is called the lapse below, inversion a lot, fumigation. So in this area is definitely bad because this would be coming close to the people around. So the main inversion or inversion a lot, the weak lapse below. So this is the one. You see this one? This one is definitely bad because it's coming very close to the atmosphere. I mean, close to the people around here. So because of this temperature increasing with this. So these inversions are bad for us. So this is the inversion in Los Angeles, California. You see that something happening because of the temperature. Okay, temperature increasing with the elevation, it becomes the inversion, and inversion is bad for us because it pushes the air pollutant to the towards the ground surface. So this is the inversion at Four Corners power plant. Excuse me. So you see what is happening is going this way, then coming down down the road is coming down. So these are kind of practical happening. So we'll example 6.3, we'll just see calculate those and make sure that whether the atmosphere is unstable, neutral, or stable. So we'll work and explain the choices. So A, B, C, I think I have the solution over here. A is delta T over delta Z. We have this, and then it would be I multiplied with 100 because I would like to make it per 100 meter. So I got -1 degree Celsius per 100 meter, so is equal to the lambda or gamma is called neutral, right? If it is equal, delta T over delta Z for the 3, so I got -1.0 1.5 degree Celsius per 100 is less than gamma, so there's been lapse rate is unstable. So the third one, C, is delta C over delta Z is 1 is greater than gamma, so it is stable. So this is good weather, this is bad weather, this weather can go anywhere because it's a neutral. Neutral means can go to the left or to the right very easily. So terrain effects, heat islands. A heat island results from a mass of material, either natural or anthropogenic, that absorbs and radiates heat at a greater rate than the surrounding area. This causes moderate to strong vertical convection currents above the heat island. The effect is superimposed on the prevailing meteorological conditions. Because of the heat island effect, atmospheric stability will be less over a city than it is over a surrounding countryside. So that's explained a little bit. Because of a lot of activities and other things, the heat generates into the city, so that's why atmosphere is always less stable into over the city than the countryside, than the villages and other things. Depending on the location of the pollutant source, this can be either good news or bad news. Good news is for ground level sources such as automobiles, the bowl of unstable air that forms will allow greater air volume for dilution of the pollutants. The bad news is under stable conditions, plumes from the stakes would be carried out over the countryside without increasing ground level pollution concentration. Unfortunately, the instability caused by the heat island mixes these plumes to the ground level. So again, heat is the main issue, right? So terrain effects, land and sea bridges. Under the staging anticyclone, the strong local circulation pattern may develop across the shoreline. The large bodies during the night, land cools more rapidly than the water during the night, and during the morning, the land heats faster than the water. The air over the land becomes relatively warm and begins to rise. So these are the terrain effects. I think I have some picture to show you. The effect of the lake breeze on stability is to impose the surface based inversion on the temperature profile. So here is the one that's happening. It looks like air over the land cools and descends. Here then goes to the land bridge, then warm air over water goes back and here. So here it is cool and here it is warm, right, in the morning time. So this is the second one, lake breeze during the day. So this is the day, looks like this is a warmer area, this is the coolest area, looks like bridge going here, warm air, nice cool air and becoming a bridge here. So land bridge and contaminant like that. So this is the fumigation. So it looks like here it is the lake. It looks like here what is happening in this area. This going temperature is going down. This temperature is going up with the elevation. So this is the wind speed. So that's why it's becoming fumigation here. So now all the atmospheric dispersion factors affecting the dispersion of air pollutants and dispersion modeling. This is a modeling showing this is the stake coming out. So it's a three-dimensional. Here is the point x, negative y, and 0. So 0 means like, so this is 0, 0, and here would be x, negative y, and z. X towards that way, y could be either way, this way to the right, and z is the upward. So that's why it is kind of positive in here. So the factors that affect the air pollutants dispersion are the emission points characteristics, okay, the nature of the pollutant material, like what kind of is it, sulfur dioxide, carbon monoxide, and others, meteorological conditions like stable, unstable, wind speed, effect of terrain and anthropogenic structures. If I have a building, higher building, then it would be abstracted definitely. So the source characteristics. Source characteristics depend on, like, say, how high it is, okay, how high it is, and horizontal air movement tend to bend the discharge plume toward the downwind direction. At some point between 300 to 3000 meter downwind, the effluent plume will level off. So meaning there will be no stake height, right? Physical stake height. So in this case, as the contaminant gases are diluted by the larger volumes of MED, they are eventually dispersed toward the ground. The plume rise together with the physical stake height is called the effective stake height. So I'll show you what is this meaning of it. So the downwind distance, the wind speed, and the directions are also has some effect on the atmospheric dispersion. So the increase in the wind speed will decrease the plume rise. So that means the stake height will be less, or effective stake height. Decrease in the plume rise tends to increase the pollutant's ground level concentration. So that makes sense. So the wind direction determines the direction in which contaminant gas stream will move across the local terrain. So the turbulence of the atmosphere follows no other factor in power of dilution. The more unstable the atmosphere, the greater the diluting power. Inversions that are not ground-based but begin at some height above the stake exit act as a lead to restrict vertical dilution. Dispersion modeling. So this is a mathematical model, definitely. Dispersion is a transport dispersion process that is quantified in terms of the source and the meteorological parameters during a particular time. The resultant numerical calculation yield estimates the concentration of particulate pollutant for specific locations and times. So first we develop the model formulation equations with different parameters. Then we solve it using boundary and conditions and the initial and boundary condition. Then we calibrate it using the known data, and if it works, then we use it in other areas. So models are usually classified either short-term or climatological and long-term. Short-term models are used under the following circumstances: to estimate the ambient concentration where it is impractical to sample to go there. The estimate of required emergency source reduction associated with period of air stagnations under air pollution episode alert condition. To estimate the most probable locations of high and short-term ground level concentration. So these are a few things that we use to use the short-term model. So the long-term model or the climatological models are used under the following circumstances: to estimate mean concentrations over a long period of time, or to estimate mean concentration that exist at particular times of the day for each season over a long period of time, as an aid for developing emission standards. So used as an aid for developing emission standard for certain areas or certain concentrations or certain pollutants. So the basic point source Gaussian dispersion model. So this is a Gaussian dispersion model. Turbulence diffusion is a random activity, and hence the dilution of the constant gas streams in both the horizontal and vertical direction can be described. The contaminated gas stream is released into the atmosphere at a distance above the ground level that is equal to the effective stake height, physical stake height plus the plume rise. Okay. So the degree of pollution or degree of dilution of the effluent plume is inversely proportional to the wind speed. Okay, so we'll see the equation, then we'll understand that. Pollutant material that reaches ground level is totally reflected back into the atmosphere like a beam of light. Mathematically, this ground reflection is accounted for by assuming a virtual or imaginary source located at a distance of capital H with respect to ground level. And this capital H, the effective stake height, we'll discuss that more. And emitting an imaginary plume with the same source strength as the real source being modeled. So here is the model equation. So the model equation is a function of x, y, and z direction looks like an h. H is the stake height. E over mu sy s z u, then e to the power, all of those. So here are the term explanation. E is the emission rate of pollutant. So we'll change it to something else in Q when we use the FE handbook for that. But book uses this one E. SY and SZ are the plume standard deviations in meter. SY in the S direction, Z is in the Z directions. I use the wind speed, X, Y, Z, and H distances in meter. E is the exponent, 2.7182, right? So you know that. So here is the model. Again, we are showing this thing. So this is the physical stake height is the capital small h, and this is delta h. This one is delta h, and capital H would be small h plus delta h. So we'll do the calculation of delta h. Here is the calculation of delta h. So delta h is a function of a lot of parameters here. The stake velocity, and the velocity at which the plume is coming out of the stake. This is the stake diameter, wind speed, pressure, and the stake temperature and the ambient air temperature. All of those are function of delta H. I don't think I have any problem to solve that, but there may be a homework that you guys have to do that using this. Okay, so we'll stop here for our next one. So this is 151. We are stopping here so we can limit the time for